This is the tutorial for Chapter 5, Section 2, titled Direct Variation. So what is direct variation? Well, anytime we've got an input that ends up making an output that is only multiplied by a constant, that would represent direct variation. So if we have an input here, and we just multiply it by one number, some sort of constant. So this is some constant or constant of variation. And when we do that, we end up getting an output that represents direct variation. There's nothing being added to that product of the input and the constant. There's just the product and the constant, or the input and the constant being multiplied. So that's what we're trying to look for as we see if these are in fact a direct variation relation. So here it asks us to determine whether each equation represents direct variation. So we're trying to put it back into this form. So write in the form, and then we just write it again, y equals kx. That's what we want. And that k can be any number. And so if it is, find the constant of variation. The constant of variation is this value. So this is the constant of variation. It's what it changes by each time when we multiply the input by this value. So basically you just solve for y. And so I'm going to divide by -8 on both sides, and I'm left with y equals. Now reduce the fraction there, it makes -1/4 x. So yes, this is a direct variation, and I know it's a direct variation because it's in the correct form, -1/4 x. -1/4 is the constant of variation. So we'll say yes, and we'll say -1/4 equals k, the constant of variation. So on this one, we've got to get x to the other side first. So you subtract that, and I'm left with this 4y equals -3x minus 5. So when I divide by the 4, dividing every number by 4 there, I've got y equals -3/4 x minus 5/4. And so put that negative sign there. So anyhow, this is not direct variation because of this right here. This makes it not a direct variation. So no, because we could say -5/9 is added to the -3/4 x. If it was just -3/4 x, that would be fine. But because we've got something added or subtracted in this case from that term, it's not direct variation. This one here, we divide by 36, -36. And when I do that, I end up reducing the fraction by 12, I end up getting a -1/3 x equals y. And this is a direct variation because it's in that form we want, y equals k of x. And where k, so this is a yes, and k equals -1/3. So those are the first type of problem that you'll end up seeing. And then here it says, suppose y varies directly with x. And that's a term you're going to, or a phrase that you might hear. And so once you hear that phrase, y varies directly with x, then we're dealing with direct variation. So write a direct variation equation that relates x and y. Then find the value of y when x equals 8. So we've got y equals 10x. Now, typically it would look like this. Okay, so what we want to do is they're telling us to put 10 in place of y and 2 in place of x, and then we can find out what k is. So I do 10 equals kx. Oops, got to put the 2 in place of the x there. So when I do that, times by 2, I'll divide by 2 to find out what this constant is, and that makes 10/2, which equals 5. So 5 is the constant I was looking for. So now they said write the equation. Well, we go ahead and rewrite it. Y equals 5x. That is the direct variation formula. Then they say, well, find the value of y when x is 8. Well, we just take that 8 and substitute it in for x. Multiplying those numbers gives me 40. So that's the second part to that problem. Well, this one's a little bit trickier because of the decimals, but same sort of thing. You just rewrite it. Y equals kx. That's what I'm trying to get. So they know what y is. Got a decimal there. Equals k times by 0.925. So I'm dividing by that 0.925 because I want to find out what k is. So great little calculator problem. So I'll go ahead and punch the numbers in there. 1.85 divided by 0.925. So nice, it comes up with a nice value of 2. So k equals 2. So all I'm going to do is add an equation where y equals 2x. Okay, so that's the problem. So now we have to substitute, because they tell us that, well, let x equal 8. So you substitute it in there and find out what the output is. The output's 16. So there it is. So those are the types of problems we'll see with that set of directions. Let's take a look at another set of problems we've got. And on this one, we've got these two, we've got to graph each direct variation equation. And so when I graph this, I'm going to start by just plugging in some numbers for x. And so I'll plug in some values for x, my inputs, and come up with some outputs. And so I'm going to start -2. So when I plug in -2, multiplying it by 5 gives me -10. So I can't really make it down to -10 on this graph. So I'll go ahead and continue on there. -1 would give me -5. I can't fit that one. That puts me right there. And then I'll try 0, and that gives me 0. And then I plug in a 1, and I'll get 5. And that point's way up here. That's about as far as I can go on this graph unless I change my intervals. So very steep line, you can see. As that line's going up, you can see how that line has a slope of 5. So that's the number that the constant variation is. So in this next one, y equals -2/5. Plugging in some numbers there, I'll plug in some x and y values. So I'm going to plug in some numbers that kind of help me out to get rid of that fraction. I'm going to try a -5. The reason I like -5 is it'll cancel out the denominator there, leaving me just with that +2. The two negative signs cancel. I'll show that work here. -2/5 times by -5. Again, the 5's cancel, negative signs cancel, so just 2. 0 is another good number. That'll make 0. And +5 would end up making a -2. And the reason that happens is because, again, the 5's cancel, but the one negative sign will make a negative. So 5 spaces left, 2 spaces up. And I got that 0, 0, and over 5 down 2. And you can see how this graph is going to end up going right through the origin again, which they all will because there's nothing being added to that equation. So you can see that's the case that you'll always see. Notice how they always go through the origin for direct variation. So let's take a look at these two problems, and I think I've got them written out over here a little bit clearer. And it says that an equilateral triangle is a triangle with 3 equal sides. The perimeter of an equilateral triangle varies directly with the length of one side. What is an equation that relates the perimeter P, the length L of a side, and what is the graph of the equation? So let's take a look at it. So perimeter varies directly with the length L. So that would be our formula. P equals KL. And so from that point, now we want to go ahead and graph that. And again, I got that because it says right here, perimeter varies directly with the length of one side. Perimeter varies directly means perimeter equals the constant of variation times by L. So let's go ahead and put some values in here. Remember, our outputs are going to represent our y-axis. So we'll go ahead and put perimeter right here, and we've got the length over here, and I'll go ahead and put some numbers in there. So let's try maybe just a, let's see here, we go with setting up a chart. So in order to graph this, we're going to end up having to come up with a value of k. So as we look at this, we see that there are 3 sides, 3 equal sides to a for the perimeter. So what we can do is multiply the length by 3, and that will give us the perimeter. So there we go. So we have now our equation, and so let's go ahead and substitute some numbers into it. So our x value is truly our L value, and our y value is truly our P value, our perimeter. And so I'll go ahead and substitute some numbers in there. And so if we go 1 space over, we go 3 spaces up. and 2 spaces multiplied by 2 gives us 6, and so on. So if I go ahead and, since I'm going to be going up fairly quickly, I'm going to call this maybe, let's go up by 3's. So this would be 3, 6, 9, 12, and so on. And let's call this one 1, 2, and 3 this way. And so if you go over 1 space, we're going to go up 3, over 2 spaces up 3, over 3 spaces up 3, and so on. And so it's important, again, to label your graph so the reader can tell which way or what kind of units I'm using to be able to draw this graph. So in this case, the graph is going to end up looking like that. Next one talks about the amount A you fill a tub varies directly. So it varies directly with the amount of time T. So A is the output, T is the input. And so now we just need to find out this constant of variation. So it says, suppose you fill 25 gallons, so 25 gallons in 5 minutes. So 5 minutes. And so if we multiply or divide by 5, that would give me 5 equals K. So now I know the formula, A equals 5T. And so now all we have to do is graph this. And so on the y-axis, we have the amount filled, and the units there were in gallons. And then here we have time, and time is in minutes. So let's go ahead and come up with a formula. We've got our T values and then our corresponding A values. And so we start with 0, we get 0. 1 minute would give us 5 gallons. 2 minutes, 10 gallons, 3 minutes, 15 gallons, and so on. So I'm going to go up by 5s this way, 5, 10, 15, 20, 25, 30, 35, and 40, and 45. And so you see how sometimes it's nice to be able to leave a little bit of space, let the reader figure out what's in between. Kind of makes the graph look a little bit nicer than like this, where here it looks a little bit clustered, too close together. And plus I ended up stopping because I figured out I've got so many numbers to write there. So if I continued on, it just looks kind of messy when you have so many numbers next to each other. So over here, I'm going to go up a little different. Instead of going by ones, I'm going to call 1 here, and then 2, 3. And the reason I'm doing that is to make it look a little bit different, so it's not just the same line going up 1 over 1 like this one would be. So here I have 1 minute of time, and so 30 seconds would end up being in between, obviously. Would be there. 0 obviously is here. And then after 2 minutes, it was 10. After 3 minutes, it's 15. 4 minutes, it's 20. And so you can see how that one ends up looking, and there it is. So those are the types of problems that you'll see on tonight's assignment. Good luck.